So there is another OpenDSS forum for discussions. So basically, just click on OpenDSS discussions. Let me do that. So when you just when you just click on write like OpenDSS download, it sends you to the SourceForge page where you click on download. It clicks you can download OpenDSS quickly, and then for OpenDSS.
Excuse me, Dr. Nalla. Can you share a screen pool? Actually, it's very small screen that we are seeing right now.
Yeah, that's the problem.
Okay.
It's like someone Vikramjit has shared the screen.
Yeah. So
I
in the
guess
meantime,
the,
you can stop giving access to other members maybe.
Now it is okay, sir. Now it is okay.
Okay. Okay. So okay, you can see my screen now, right?
yes, sir.
Okay. Okay. So basically here you can write just OpenDSS discussion, and then it sends you to this page in SourceForge where you can look into. Where in SourceForge, if you want to have any, like if you have any question on any topic, you can just search like regulator like IEEE 123 bus, search it here, and then you can find a lot of threads. And you can go through these threads, or you can have an account here in SourceForge and just ask different coders or whoever the developers are in OpenDSS, and they can answer you within some time. So if you are into doing research on OpenDSS and distribution system simulations and everything, you can ask questions here. And okay, so the next part was modeling, right? So modeling of distribution system. So I'll give you an example of a distribution feeder in OpenDSS where I will talk about how the lines are connected, and lines are connected, what the different buses, how buses are modeled, transformers, loads, capacitors, voltage regulators, everything. So let me do that. Okay, so now once you have downloaded OpenDSS, you can just um, open the software OpenDSS. So you can see my screen, right?
Yes, yes, it's
Okay,
visible.
okay, okay. So once you open the software, here I'm like I will go through a typical distribution unbalanced feeder, like unbalanced distribution feeder, which is the 13 bus feeder, IEEE 13 bus feeder. So you can find that in test cases, IEEE test cases. So uh, whenever you download OpenDSS, OpenDSS will be saved in a folder, like in a particular folder. Generally, it's program files in C. So if you go into C program files, uh, here I already have that, but um, if you go into C program files, you can find OpenDSS here. Go into OpenDSS folder, and then if you go to IEEE test cases, here just click on 13 bus system, right? 13 bus folder. Now in 13 bus folder, you have two files: this IEEE 13 node circuit and IEEE line codes. And so all OpenDSS files are named as DSS files, as you see on the right hand side, right? And if you open this IEEE 13 node circuit, so it opens up like this, right? So now I'll just go through the code for a bit and then try to explain what each of these things mean. Now, to understand this whole code, I'll just, what you can do is you can, so basically this code has to tally up or match up with the basic IEEE 13 node system, right? So if you go to, so all these IEEE test cases are present in this, um, are given in this website, which is PES resources, right? PES resources distribution feeders. So it sends you to this into this IEEE PES resources. So IEEE PES test feeder. I'm putting that in the chat. So if you go to this resources website, then you can see this all test feeders, right? 1991 original test feeders, 1992 test feeder cases. So these were originally created in 1992. So you can find this 13 bus feeder, right? If you click on this 13 bus feeder, then you get a zip file which gets downloaded, right? Now inside that zip file, you can find this particular file which is named as the IEEE 13 node feeder. So it looks like a docx file, like a Word file, and it explains, it shows how each of the nodes are connected. This is the basic 13 node system. So it's a very highly unbalanced system, and so bus 650 is the substation node, and then you have a voltage regulator, right? So this voltage regulator kind of boosts up the voltage, and then it is connected to different nodes. Then you have 632, 633, 634, and all of this. And this is unbalanced, as well as it is multi-phase feeder. So basically, there are some nodes which don't have all ABC phases. Right? There can be a single phase nodes also, and there are the other are definitely 3 phases, but you can also have 2. I don't exactly remember if there is 2, but there are definitely single phase nodes as well. Now, whatever is written in this docx file, that has to exactly match with the OpenDSS file, OpenDSS model, right? So you see that how it is explained. So first, they define some overhead line configurations, right? So what I mean by this is that there are 5 type of overhead line configuration that they're saying. Like there is, I mean, these 5 type of overhead lines are also used in this particular model. So there is this line code. There is this particular line which is coded as 601. It can be 1001 also, right? But they have just given it at 601. So this overhead line has all ABC phases as well as the neutral, and it shows the line configuration, right? So it's an ACSR type of conductor, and the spacing ID is given. So all this spacing ID, everything will make some sense in a certain in a bit. And then the neutral is a different ACCR conductor, which is now this ACCR conductor names that you see, it differs with respect to what the GMR value is, right? Geometric mean radius, and what is the diameter of the conductor, and all the specifications you can find it online. So these are different overhead line conductor configurations. Then you have underground line configurations. Like there are 2 types of oh, there is another one that you can see here, that in overhead lines, 603, 604 are two-phase lines, right? CBN and ACN, whereas 605 is a single-phase line, right? And in underground, there are two types of underground lines as well. Like there is 606, which is a three-phase underground line, and 607 is a single-phase underground line. And then what is the cable configuration? Like the cable conductor will be exactly what this code actually means, um, and you can find it, online, like um, how what each of these configurations mean. Then you have line segment data. Line segment data means that what it says is node A, node B, length, and configuration, right? So it says that 632 should be connected to 645 by the conductor 603. 603 is already defined up, right, which is CBN. And the length of the line is 500 feet. So now this line segment data will explain you how each of these nodes up here are connected with each other. Each of these nodes will be connected by a certain conductor type, and the length of the distribution line is also given, which is given in feet, right? So basically what you do is when you have this line configuration data, you follow this line configuration data, you get the R and X values, right? Resistance and reactance values, which will be per mile or per feet, whatever. And then you multiply by this length. Then you get the actual reactance and resistance value of the distribution line connecting two nodes, right? Similarly, you get this line segment data connecting different nodes. Then you have transformer data. Transformer data means, there is a substation. So there are two transformers, right? One transformer is at the substation, which brings that voltage down to 4.16 kV or some other voltage, and there is another transformer which is between 633 and 634. So these two transformers are explained, like what is the high voltage base value, not the base value but rated value, low voltage rated value, RNX percentages and everything. And it says, like, it's in delta, the substation secondary side is in Y formation, it's in star formation. So all of this is written. Then you have capacitor data as well. So you see that there are two capacitors which are connected in the system, right? Which is at 675 and 611, and it also shows what is the capacity of each of the. And I think 611 is a single phase line, right? So it's a single phase node. So which is phase C is the only phase that you have at 611. So 675 and 611 are exactly here, right on the right hand side and on the left hand side. So these capacitors, why they're placed at the periphery of the network? Because at the periphery of the network, you'll have the lowest voltages, right? So when you have low voltages, in order to boost up that voltage, those two capacitors are placed. Now, I'm just giving an example. You can place the capacitor on other positions as well, but just for your clarity. Then you have regulator data, right? Regulator data, it connects 650 and 632. 650 and 632 is here, right at the top, right? So there is this regulator that I was talking about, and this regulator kind of boosts up the voltage, and it also shows what are the phases, connection, bandwidth, PCT ratio, compensator settings, ABC, RNX. Now, for distribution systems, I would like to recommend this book by Karsting, which is on distribution system modeling and analysis. So if you follow that book, you'll probably understand distribution system pretty well, and it's a very well written book. Let me find that. yeah, so basically you should follow, like if you are working on distribution systems, you should definitely uh, follow this book, which is Kirsting's book. Put this in the chat. Now, what each of these conductors configuration mean, or what, how these regulator configurations look like CTPT compensator, what does this mean? All of these are explained, as well as how to model distribution system properly. Everything is written there. And then you have spot loads, right? Spot loads meaning loads which are connected to each of the nodes. Now 634 is like there are PQ loads, it's in star formation, and then you have all the exactly the active and reactive power loads that you have for each of the phases. So everything is defined in this particular document. So which nodes are connected, how each of the nodes connected, what is the length of the line, what is the configuration of each line, the configuration of regulators, transformers, in which nodes loads are placed. There is a distributed load as well, which connects two nodes, right? And then, so basically, you have all this data. And then they also give you impedance data. Impedance data I was talking about, the R and X, resistance and reactance, ohms per mile, right? So when you have a configuration 601, so suppose where is configuration 601? So 601 is this configuration, right? And 601 connects 650 and 632. And the length of the line is 2000 feet. So 650 and 632 is right up here. So the substation end to the first node, right? So this particular line has a configuration of 601 and the length of the line is 2000 feet. Now, if you come here, 601 configuration RNX values are already given here. So, and it looks a bit different, right? It looks like a 3x3 matrix where this particular elements 2 crossover 2,1 3,1 3,2 are not given. It's symmetric. So basically, it's a 1 2 equal to 2 1 3 1 equal to 1 3 and all of that. But so basically those two nodes are connected by 601 over 2000 feet of length, right? So you have these RNX values, you get these RNX values and then just multiply that with the feet. Now it's per mile. So what's how many feet is that in 1 mile? So I think it's 1760 multiplied by 3 or some 5,000 something, 5,600 or something. So you just take that ratio and then multiply with the RNX values. Now this RNX values as well as it gives the microsiemens, which is admittance, right? So it's B, not admittance. It's admittance, but B is conductance, right? And so what this represents, it represents the line charging capacitance between, in a distribution system. Now line charging capacitance is pretty small. It's very small, so you can pretty much neglect this part. But when you model distribution systems, you can kind of neglect this B part, because this line charging capacitance is very important for transmission systems. The reason is that transmission systems are long, it has a very high voltage, right? So your charging current will be much more, because it's like charging current is equal to omega C V, right? So it's like so your capacitance, the length of the line, the more the length of the line, the more the voltage, your charging current will be much more. So you cannot neglect B there, but here you can kind of neglect B. And so you take the Z values, which is R and X values, So each of these configurations, line configurations, will have that R and X values, right? So you just take these R and X values and that multiply that with the line length, and you'll get the R and X value between two nodes, right? And then you have this power flow results. So once you put down all this configuration, like how each of the nodes are connected, then you'll get this power flow results. Now, whenever you do any kind of research work or any kind of modeling, and if you got a standard IEEE test case power flow results, you have to match your model results with the power flow results. Then only you can say that your model is validated. So if you have an OpenDSS model in 13-bus system and you take exactly the line configurations, the same exact connections and everything, RNX values and everything, and at the end of the day, if you can't reproduce the same power flow results as it is given here, then you cannot validate your model, right? There is some bug or something you're doing wrong. So these power flow results will show you the voltage profile, right? It shows you how the voltages look like, what's the voltage regulator data. So at the end of the day, how the taps look like for each of the voltage regulators and all of that. So the reason of like showing all this, use docx document is whatever is written in this document, you have to exactly copy that in OpenDSS, right? So now if I go to OpenDSS, so you have this in OpenDSS, so firstly, this circuit is defined, right? In circuit, so this new circuit, it's named as IEEE 13 node circuit, but you can write it as IEEE 13 node bus circuit or something else. It doesn't matter. And so there is this source bus. Right now, the angle of the source bus is 30 degrees. So it's like in the source bus is basically the substation node. Now it says that advance angle 30 degrees. So result degree with published angle. So angle here is 30 degree means, your reference angle at the phase A is 30 degrees. Then phase B will be 120 apart, right? It will be minus 90 degrees. And definitely your C phase will be minus 210 degrees, something like that. So when you run power flow, you can just set this angle to be 0, and then, you'll get the way you write. Your VA will be at 0 degrees, bus angle VB will be at minus 120, and C will be at plus 120. And then it's an infinite source, so they kind of stiffen that with a very high short circuit MVA. And then you have all these definitions in OpenDSS, exact definitions that are present in that docx file. So you have this transformer which connects, which is a, so what these things mean is that you have this transformer dot sub. So it's named as a substation transformer. It has 2 windings, it has 3 phases, and it connects source bus to bus 650. The source bus is on the delta side. The 615 node is on Y connection, and then you have KV levels, and R and X values are put exactly. You have to kind of match that with the doc file, and then you have this regulators defined, right? So in regulator, so this is regulator 1, regulator 2, regulator 3. So regulator 1 is connected to 650 to RG61, right? And then suppose if I show you what this actually means. So you have this regulator data, right? So regulator data will have 650 to 632, right? It says where the regulator data is placed. But OpenDSS has created a fictitious node, right, which is RG60. So from 650 to RG60, you have this regulator 1. From 650.2, so 650.1 is phase A, 650.2 is phase B, and 650.3 is phase C. So each of these phases are connected with each other by a regulator, and it also shows, the CTPT ratio, regulation voltage, load loss, and all of these things are defined. And there is another transformer which is present, which was present here, right? Which is this 500 kVA, which was present between nodes 633 and 634. So this is again defined here. So you have to define all this, all these elements. Whenever you see this exclamatory sign in front, so it means that it's commented out. It's exactly like writing percentage in MATLAB, or put a hash in Python and all of that. So basically, if you want to comment things out, you have to put this exclamatory sign in front. So this transformer is defined, and then it says in line codes, it says redirect IEEE line loads line codes.dss. What it means is that this is kind of redirect kind of means to call another file. So this file node circuit.dss calls another file which is IEEE line loads line codes.dss. So where will you find that? You'll find exactly in the same folder as it was. So basically, if you go to IEEE test cases, go into 13 bus system, then you'll find this IEEE line codes, right, which is another DSS file. And if I open it, then it will show, all of these different line codes. Now, the line codes are defined here is for 123. There is also definitely a 13 bus system also. So this is for 34 node feeder. So this file contains line RNX values, like line configurations for all kinds of IEEE test cases, right? So this is another for 4 node system, this is for 13 node. So this is, so if you see redirect, that means it calls this particular file again. So the node circuit.dss calls this particular file. And then you see this line code is defined here. So it's like 601 that I was talking about, 601, 602, what are the different phases. The R matrix, X matrix, and C matrix are kind of defined here. So it should be exactly equal to what you see in the docs file. Let me check if this is actually needed. I think this is not needed at all, because then again, they define the same line code, right? And so these line codes are defined. All these line codes are defined here. And then what else? You have, I think this is an underground line. Underground line geometry. I think it's just a comment. This part is commented out. MTX. Okay, so all this, after all these line configurations are defined, and this should be exactly equal to the manual, then you come into this load definitions. It means load definitions means you define certain loads, and you then, so suppose I define a new load which is 671. It is connected to bus 1, means it is connected to this bus which is 671, and it is connected to all the 3 phases, right? And so it has dot 1, dot 2, dot 3, means it is connected to all the 3 phases, and it's a delta connected load, and you have the kV, you have kilowatt, you have kVr. Now we can just check for one case. So suppose this particular thing, right, which is 670. So at 671, 2, and 3, there are different kinds of different there are different values of load. So basically, in phase A, you have 17 kilowatt, 10 kVr. Phase B, you have 66, 38. Phase C, you have 117 and 68 and 670, right? Six 70. 670 ABC. Oh, this is kind of, oh, it's here, right? So you have a distributed load here, which is a different kind of load, and the distributed load is, you can take it as a spot load, but it acts as a spot load at 2/3 of the line, right? And why it is taken as 2/3 of the line is again explained in casting a bit. So you already have this thing right here. So by distributed load data, what they have taken is that they have taken another fictitious node 670, which is placed at 2/3 of the line between 632 and 671, and they have placed this exact load at that particular point, at that 2/3 of the line, because it's a distributed load data. So so then you can just match with the loads here, and then you have two capacitors which are connected at two nodes, and then define the kV levels, line definition. So here I was talking about the line, because why do you don't need the redirect? Because if you see the line definitions here, it is this line connected between 650, connecting between RG60 to 632, and then it also shows the line code, which is MTX601, right? The MTX601 is already explained. MTX601 is already shown here. So you don't need this line codes.dss, but if you have it, it doesn't make any change, because whenever OpenDSS runs the program, it will definitely go into this particular configuration, which is MTX601. So so then once you define all these lines, so here length is 2000 feet, right? And then you have kept the unit as feet, so it will automatically convert that with respect to mile and feet and everything. Then you have a switch which is kind of connected. Switch is yes, so that means it is enabled. And you have three voltage bases, right? You remember that in the substation you have this 115 kV, right, on the primary side. On the secondary side you have 4.16 kV. And just after the transformer, so if you see this transformer, which is between 633 and 634, on the 634 side you will have a very low voltage, which is 480 volts, which is 0.48 kV. So that can be seen. Where is the transformer? Yeah, so you see this transformer definition, right? On the 634 side you have this kV level, which is 480 volts. Now this is what it does. So this is the primary and secondary side definition. So you see on the primary side, so this is what's called the primary and secondary distribution system. So on the primary distribution system you have the 4.16 kV level, right? And then you have this transformer. This transformer can be thought of a service transformer or like a house transformer, which brings the 4.16 kV to 480 volts. Now from the secondary side of this transformer, you can connect like 10-15 houses, or all the customers get their own service. So that is where you have the secondary distribution feeder. So from 480 volt onwards, if you have like another connection which connects like 10 houses or 15 houses, then you will represent, that is the low voltage distribution feeder, or the secondary distribution feeder. And then 4.16 is on the primary. So when I say primary distribution feeder and secondary distribution feeder, it doesn't say, I'm not talking about primary and secondary of a transformer. I'm talking about voltage levels. So even when you are distributing power from the substation end, we like people power engineers distribute power on a higher voltage. It can be 4.16, it can be a bit more. But when you have to transfer that power to houses, just at that point, you have to put a service transformer on the pole top and then bring, it can be pole mounted or wherever it is. And then you have to bring that, high voltage down to 480 volts or 240 volts and all of that. So generally it's a center tap transformer. I mean, I'm not going into much details, but from that transformer onwards, whatever connections you have to each of the houses or residential customers, that is known as the secondary side of a distribution feeder. So utilities generally don't have much visibility on the secondary side, and on the secondary side, you know, there can be huge voltage dips and voltage boosts that are not visible to the utility. So that is a different kind of a problem, but I'm just trying to explain about what 480 volts really mean. So once you have this, so this acts as a service transformer. If you connect like 10 houses, if you model 10 houses in OpenDSS and connect it to 480 volts, then you can say that, this is a, in 13 bus feeder I've created in the secondary, you know, distribution feeder, which is, connected from the house transformer to 10 houses. So you have this voltage, you have to define voltage basis, because if you don't define voltage basis, then OpenDSS cannot convert that in per unit formulation, in per unit form. Then you have calc v. So calc v solve, all of what it does is that it kind of solves the power flow. Then you have this CSV file. So this bus code CSV file, it's a particular file which is given by OpenDSS. So it comes with every test cases, I think, and it shows it shows a plot of the whole feeder. So it looks like, so I'll show you about what it is. Okay, so now you have this. Once you have this model done, then what you do is just run a simple power flow, right? So if you press on Control A, then do selected, then you see this thing coming up on the left hand side, right, which is a circuit summary. Now it's very hard to understand what each things mean. So it shows anyway it shows a, it says all solved, and then it's a solution mode is snap. Solution mode is snap means it's a snapshot solution. So what I mean by snapshot solution is that is what we, whenever we code power flow, it's a snapshot, right? So snapshot in the sense that you have defined loads, you have defined, voltages, initialized and everything. When you do Newton Raphson, it's just take that particular loads and then takes certain amount of iterations and just solves it, right? So it also says total number of iterations, none of that. So it's a snapshot in the sense that you take a particular snapshot of a power system profile, and then power system load profile, and then solve power flow for it. And then you have, max min values of voltage, you have active reactive power, MVR. So it says that, how much of active power is drawn from the substation side. Similarly for the reactive power, how much is the active losses and all of that. And now if you want to see even more details, right, how the voltages look like. So if you go to this show tab on the top, so in the show tab, you can, if you click on summary, it will show this exact summary that you have. But if you go to voltages, now in voltages, you can see line to neutral voltages, then line to neutral nodes. So if I click on LN nodes, which is line to neutral nodes, so then it looks like this, right? So you see the source bus is like 30 degrees advanced, right? So 30 degrees advanced, 90, 150, and it shows what each of these voltages are. voltages for each of the nodes, right? And then you have this RG60. RG60 is the one which is just on the secondary side of 650, right? So if you see at 650, the voltage is almost 1 per unit. And then again, you have this huge boost at RG60. This boost was coming off because of the regulator had a tap, right? It tap means it tap settings are kept in such a way that it boosts the voltage. Because this voltage has been boosted up in the in the substation side, then you have, you know, the, if you see the periphery ends, the periphery ends voltages are just above 0.95. So there is this um, another standard, not like a standard, but a kind of rule that we follow in distribution systems is we try to keep bus voltages within plus minus 5% of the substation voltage. So we try to keep the bus voltages within that band of 0.95 per unit to 1.05 per unit. So this is in steady state. I'm talking about steady state. Obviously, if you go into it bit details, then you can find standards where, you know, under emergency conditions or under different conditions, how much voltage dip or voltage boost you can allow. That is that you can find it online, but it will be definitely below 0.95. I mean, it will say that you can go below 0.92 or just stay above 0.9 per unit for this amount of time and all of that. So those are like standards that are for power engineers, but just for your knowledge, just know that for steady state, we try to keep bus voltages within that plus minus of 5%. So if you see this particular node, which is at 684, so this comes pretty close to 0.95, right? And the reason of putting why this is just above 0.95 is because of that capacitor which is placed. Similarly, at 611, you remember that there is this capacitor which is placed in 6911. So now, what else can you see? So if you go to the show button again, then you can go into powers, you can go to currents. If you go to currents elements, then it will show, you know, how much the current is flowing in each of the lines or each of the elements. Then you can also show powers. So in powers, it will show kVA elements. So it will show how power is flowing through each of the elements, right? And it also shows power factor on the right hand side. And what else? You have energy meters, you have taps also. Here you can check the taps. So the taps is kept at 9, 6, and 9. So if you remember that this tap positions doesn't match with IEEE test case results, right? So we will try to see if we match the positions, does power flow hold or not. I'll come to that as well. So this is in under show button, you can see all of that. But you can also export the same data to a CSV file. I mean, that notepad file, txt file doesn't make sense because you can't use that file, right? Now suppose if instead of 13 bus system, you have like 2000 bus system or 10,000 bus system, then you want to visualize all bus voltages throughout the feeder, right? So then how can you do that? You just export that voltages. Okay, that if you export that voltage, that will be exported in this particular location, which you can define on your own. But here, if I go to this, if you see here, if I go to this particular folder, yeah. So if you yeah, this is the one. So you can export voltages, currents, powers in CSV file. So once you export this particular file, you see that it shows magnitude, angle, per unit values, and everything. And if you can extract out how far it is from the substation in terms of distance, then you get, suppose it's a 2000 bus system, right? So you will have like 2000 rows or 2001 rows in the CSV file. It will also have a distance, right? In, suppose here in column O, then you can just plot it. Like you can just put in Tableau or other, you can just use Python or whatever and see how the voltage looks like over distance, right? It will drop, it will rise, it will, and then you can, in the, once you visualize, you can check, at certain nodes the voltages will go really down, some voltages can go really up due to presence of solar panels. It depends, like where, whatever you want to. So once you have that CSV file, you can use that CSV file to visualize everything. So that is what generally utilities do. They run power flow simulations, export that in a CSV file and try to visualize. So similarly, you can export currents, you can export powers, you can export losses, whatever you want. And yeah, so suppose in this model, it's, the angle is already advanced to 30 degrees, right? If I keep it at 0, how does it look like? Keep it at 0, Control A, and do selected. So now if I show voltages, so now see the voltages are kind of, it's kind of okay right now. So it's 0 degrees, minus 120, 120, right? And so then you can check, how the voltages look like. Now the other thing is, so if I show the taps now, I think the taps are still 969, right? Now, when the taps are at 969, what it actually means is, this is the position 9, and then you have this tap. So you have regulator 1, reg 1 node, which is, so reg 1 node, how much is the voltage at reg 1? Yeah, so regulator 1, which is regulator 60, right? RG60, you have 1.056. So how much does it get boosted from 1? So at 650 secondary, at 650, you had just 1 per unit. And then you have this huge boost at RG60 phase 1, you have 1.056. So what it means is that when you put at tap position 9, then you get a boost of 0.05625 per unit, right? So it means that each tap position improves your voltage in 0.00625 per unit. So what it means is that so if you multiply this 0.00625 by 16, then you will get 0.1. So what it means is, let me show that in a calculator. So you have 0.00625, right, multiplied by 16, then it becomes 0.1. So this is how voltage regulators are designed. So you have 16 taps which can go up and 16 taps which can go down. So basically, you have this ability where, so you have this 32 taps, and 32 taps will help you to boost up and boost down. So if you have that 0.00625 multiplied by 9, so this is the amount of per unit voltage that will get boosted, right? So this is what happens in RG 60. When you have at tap position 6, it will be boosted by 0.0375. So if you just multiply that with 6, it will be exactly that. So in voltage regulators, you have 16 taps for boost up, 16 taps for boost down. and each of these, so for boost up you can go to 10% of 10%. You can boost 10% voltage, you can boost down 10% of voltage. So whenever you have a regulator, like it does in that way. So if the position had been suppose 10, your second your voltage would have been like 1.0625, right? Now so right now, so let's do one thing. So you remember that in docx file we had this power flow results, right? And in power flow results it says that you have to keep the tap positions at 10, 8, and 11. So if you want to keep at 10, 8, and 11, then how the voltages should look like. So let us try that. If we, so there is this alternate solution script, right, in OpenDSS. What it means is that this is scripted out, this is commented out, but we can force the taps in the regulators to be at a certain value. And then once we fix that taps, and let's see if the power flow results match or not. Because once the taps are fixed, then we are saying that we are boosting the voltages by the same amount as it was done in the docx file, right? So then the OpenDSS results and the IEEE test results that you see in the document file will be should be exactly same. If they're not same, that means there is an anomaly, there is a problem in your own models, right? Because these are voltage controllers, these are devices. This regulator is a device which boosts up or boosts down the voltage, so it controls voltage throughout the feeder. Now if the taps are not similar, then you won't get the same amount of voltage throughout the feeder, right? But if the taps are similar and you have the same capacitors present which are on in both the models, then your models should match, right? So now if you see this voltage regulated in the manual is 10, 8, and 11. Now if you multiply 10 with 0.0062, it will come up to be like that. So here the tap goes from 1 to 1.0625. If it is, so what was the next one? It was 8, right? If you multiply 0.00625 by 8, 0.00625 by 8, then it becomes 1.05, right? Which is exactly here. And if it is 11, then you have 0.06875. So it exactly shows up here. So let's keep this Control A and do a selected. So once you do that, um, let's see voltages. So you see the voltages had boosted up, right, from 1.0625, but it's not exactly 25, but it's pretty close. Now let's check, say, bus 684 data that you find in OpenDSS, and let's check this one. So it's 684. So at 684, you have this 0.988 at phase A, and at phase C you have 0.976, right? So at 684, it's like 0.9874 and 0.976, which is like very close, pretty close to each other. So you can pretty much say, the voltages kind of match with each other. So this is a kind of validation that you have to do every time if you do any kind of modeling in distribution softwares. So it can be OpenDSS, it can be GridLab-D, or it can be any other modeling software. So whenever you have different kinds of softwares, you model the whole system and then you try to match up with the one way you can match up is, suppose you are in the utility, right? You have certain meters and you have meter data over a certain year, like previous year, and you model the whole system in OpenDSS and you run power flow. And if the power flow kind of matches with the meter data, obviously the conditions have to be exactly same, loads have to be exactly same, configurations have to be exactly same. Now, if under those situations, if the power flow results kind of match with the meter data, it won't exactly match. But if it matches, then you can say that your model is correct. So this model looks correct as for now because the voltages are pretty much close, right? So this is the kind of validation that you should do. Okay, I think like we can take a break for a few minutes. We are right at the break of 1 hour, and then we'll start after some time. We'll now talk about different control modes and different control architectures. And I would try to put more of hands-on kind of things like this one. I won't go into much details into theory and all of that, but because that is something that you can obviously gain knowledge into, but hands-on, I think, is much more important right now. Okay, so
Yeah,
I'll rejoin.
definitely. Yeah. As you
Mhm.
said, we can take a break. Yeah, after
Yeah.
some time. Okay. Hi, Dr. Neela, can we start? Restart the session?
Yeah, yeah, sure.
Okay.
Okay, let me share the screen. Yeah. Can you see my screen now?
Yes, yes, it's visible.
Okay, so these are the same pictures that we saw. So basically, how each of this um, how each of these systems are connected to the distribution system. You have cyber, you have SCADA, you have microgrids, microgrid management system, DERs, optimization, distribution optimization, and it covers different domains. But here we are trying to look into specifically for distribution system modeling in uh, this particular 1 hour course. So um, there are different DER control modes that we have in power systems. So now droop control mode, as you know, it's a very classical um, control mode for synchronous generators in power systems. So basically it kind of controls active power flow depending on the frequency, and balances reactive power depending on the voltage. So um, this kind of follows the P theta, active power pass angle and VQ coupling that we have in in transmission systems. Um, we do also operate inverters sometimes on this mode. So this is a very classical control mode, Drew. Then we have power factor control mode. So what I mean by power factor control mode is, the capacitors that I was talking about. There are two there are two main functions of a capacitor, like in distribution systems. One is to correct power factor, and the other one is to improve voltage. So whenever you see, if you see any kind of feeder model, you'll most of the times you'll find a huge capacitors at the substation side. So its main function is to correct power factor. So that is what um, it does. And then there are some capacitors which are present at the periphery to improve the voltage. But I'm just giving an example. This power factor control mode is not for a capacitor. So in DERs, like if you have PV and battery, you connect that PV and battery through certain converters to the grid, right? And those converters, which are power electronic converters, they are able to, sense they are able to modify active and reactive power instantaneously. So why it is instantaneously? Because it's a power electronic device, and generally there are two control groups on the grid side converter. So both of the control loops will have a time constant of 1 millisecond and 10 millisecond in that range. So whenever you change this reference setting of active power or reactive power on the grid side converter, which is connected to a renewable source, it can be PV or battery, within 10 milliseconds or 1 milliseconds, they can catch up with the step change in reference. So that's why I'm talking why instantaneous it is. So if you keep the mode in such a way that sense power factor, or sense how much of reactive power you have to send, or how much of reactive power you have to send or absorb or whatever. Obviously when power factor is at 1, then you don't inject any reactive power, right? But that way it can control power factor. Voltage control mode, it's a bit different. So um, you the grid side converter, what it will do is it will sense the PCC voltage, which is the point of common coupling voltage. It will sense that voltage and send it back to the control management system, where this this sensed voltage is then compared with the reference voltage. Suppose you have a PV inverter and you want to maintain the PCC voltage at 1 per unit. Now, since PV is connected, the voltage will boost up or boost down, depending on it. Won't boost down, but it will generally boost up because PV sends active power, right? And that active power will boost that voltage. Um, so the voltage control mode works in this way, that it will sense the PCC voltage and then it will compare that with the reference voltage and it will send, I mean, it will inject or absorb reactive power in order to control the voltage. Now, all these control modes are explained, in literature, and you can find these are pretty much explained in literature, and how to use these control modes on different operations, that is explained in IEEE 1547 standard. So IEEE 1547 is a very it's a standard that we have to follow whenever we design or operate DERs connected to the grid through a converter. So you can find more details, voltage right through, how much of voltage we can, how much is the minimum voltage that we have to allow, and all of that. Then we also have frequency watt control mode. So these are different control modes which come up with different configurations and are different situations. So frequency watt means, it's the same. So it's a very, so it gives a grid stability service, right? So when you have like huge wind farm, you can control the active power injection from the converter, from the wind farm grid side converter, in such a way that it helps in stabilizing the system. So what it will do is, when you have an active power reference at the grid side converter, that active power reference can be represented as a function of frequency. Now, if we represent that reference power as a function of frequency, then what happens is that we are trying to inject active power following that reference power curve, right? So we can inject active power in such a way that it mimics a frequency related curve. So it's a function of frequency, right? So so that way we can stabilize the grid. Generally, it's a very, it's a transient stability or transients kind of operation. So we can improve the dynamics of the system. We can improve dynamic stability of the system. So whatever we have been doing right now in OpenDSS, those are steady state power flow analysis, right? Steady state meaning that loads are fixed, everything is fixed, there is no transients happening, just solve power flow. But in real time, you have a lot of dynamics going on in the system. Active power, reactive power, loads are always changing all the time. Now, if you don't stabilize the grid under such dynamics, then it's very hard to operate it, right? Just for an example, you are in your house, you are going out, coming in, going out, then you are like switching on and switching on the lights and fans and everything every now and then, and nobody is questioning about, okay, you can't do that right now because you're removing load or you're increasing load at this time of the hour, right? Nobody questions that. Why is that? Because this amount of disturbances can be taken care of from the power system side, because this kind of disturbances can be taken care of by the inertia of the system, which is kind of saved in the rotational energy of synchronous generators, right? So these disturbances won't matter much because the inertia of the system is huge. Now, if the inertia of the system is not huge, or if you are not able to control power flow depending on frequency, then you have problems, right? So this is what dynamics really mean. Then you have volt watt control mode. So volt watt control mode is voltage and active power, right? So in transmission systems, as you know, that R by X ratio is pretty less, right? So you have huge coupling between active power flow and bus voltage angles, and similarly for reactive power flow and bus voltage magnitudes. But in distribution systems, you can have the R by X ratio is pretty much is considerably high. So that coupling doesn't work. So if you inject active and reactive power, it will it, even if you inject active power, it will improve the voltage also pretty considerably. This is because of the presence of R values, like higher R values. So there are some DERs where you can control voltage based on how much of active power you inject to the grid. So those are those operate in volt watt control mode. Reactive power support mode is again another ancillary service that DERs can provide to the grid. So if you if you have if you have to do power factor control, or if you have to boost the voltage at certain section of the feeder or at certain section of the power grid, then you can tell that DER that inject or absorb reactive power, and then you can stabilize the grid according to the needs that according to the needs that you have, right? So these modes are pretty common, like you can find that in literature, and if you have to operate DERs on this mode, then you have to follow the IEEE 1547.8 probably. Or you can just search IEEE 1547 and it will be available online in IEEE. So okay, so the other way is, so there are two important control modes again for inverters, which is grid following and grid forming. So grid following means that you have a converter which is connected to the grid, and but it just follows the grid. So it just follows whatever the grid voltage is at its terminal, and then it gets connected to the grid. It is not affecting the frequency. It is not affecting any other things. So it is just changing its own current injection, and that's how it is injecting active or reactive power to the grid. Grid forming inverters are a bit different. Grid forming inverters means they kind of act like a synchronous machine, right? So they have the ability to to control frequency or control active power flows in the system. They can stabilize the frequency, or they can, under certain situations or under resiliency conditions, when the grid is off or a certain section of the network is not connected, then it can take care of the grid, it can take care of the frequency and everything. Okay, so um, we'll talk briefly about this control architecture as well. So, so in distribution systems, we have generally three or four, like four kind of control architecture in DER-rich distribution systems. Now, the most common ones are the centralized and local. So, what I mean by that is, so if you look into any utility in India or US or wherever, they will have generally centralized or local control techniques. What I mean by that is, suppose in IEEE 13 bus feeder, right? You saw there are two regulators. There's this substation transformer, and there is this regulator, and then there are some capacitor banks, right? Now the capacitor banks can be modeled in OpenDSS in such a way that you sense the voltage. If the voltage is down, then switch on the capacitor. If the voltage is up, don't change the status of the capacitor, right? So that is a local control architecture. Why? Because it is local measurement, local computation, local sensing, everything is local. So there is this management system, capacitor management system, let's say. So there is this agent which sits on the capacitor, and then that agent senses local bus voltage. If the bus voltage is less than 0.96, switch on the capacitor. If the voltage is beyond 0.98, then switch off the capacitor. Otherwise, don't change the status. Like if it is on, keep it on. If it is off, keep it off, like that. So you can have this kind of local control architecture, right? Where it senses local voltage, not even voltage, it can also sense current, power, whatever it is. So it is based on three things: local sensing, local measurement, local computation, and local actuation. So you sense something locally, compute something locally, and actuate something locally. Actuating sense in meaning that you switch on or switch off, whatever actuations that you do, right? Centralized is a bit different. So centralized means that you have suppose multiple agents throughout the system. So centralized means um, you sense measurements. You have suppose 10 agents in the system. You sense measurements or sense whatever. Send it back to a centralized unit. Okay, that unit will do all kinds of computation. That unit will take 10 measurements or whatever measurements it is getting from 10 agents. It's take those measurements in. That centralized unit will do certain computations. It can be optimization, you know, control, whatever it is. It will do certain kind of computation, and after computation, whatever set point that it gets, suppose after computation it says that, okay, after my computation I get that, you know, the tap setting of this regulator should be by this much, this capacitor should be on, this capacitor should be off, tap setting of this one should be like this. So they will send those set points back to those agents, right? So those agents, then whenever they receive those set points from the centralized unit, they will actuate that. So centralized means that you gather data throughout the network, bring it to a centralized unit. So the centralized unit that I'm talking about, generally in distribution systems, it would be the distribution management system or the ADMS, which is generally present at the substation end. So they will gather data throughout the network, bring it to the ADMS. In ADMS, there is this optimization solver or whatever there is, and they will compute decision variables. Decision variable meaning that, you know, what apps should be, capture keep on or not, what should be the set point of the, what should be the set point of battery, and all of that. And then they will send that set points back to the agents. Now, so what it does is, so for this you should have a dedicated communication infrastructure, right? Each centralized architecture, you should have a very extensive communication infrastructure. And if any one of the fails, if any one of the communication channel help fails between one agent and the ADMS, then the ADMS may not be able to come up with a solution, right? So that is a disadvantage for centralized solutions. Obviously, you know, I'm giving an example, but they can still operate on that. On certain situations, they can take an estimate or whatever. But what I'm saying is, there is a possibility that, you know, there is an important information that they need to gather, and they are not able to do that at the ADMS level, and they could not come up with any solutions. So this is kind of termed as single point communication failure. So the communication infrastructure has to be, you know, extensive, it has to be dedicated, and it has to be available all the time. So this is one disadvantage of centralized. Decentralized means that you have this architecture where it's a cluster based architecture. So suppose you have this 13 bus system, right? And in 13 bus system, you divide the 13 bus system into three agents, like three agents. Now three agents will have, one agent will have 3 nodes, another agent will have like 5 nodes, and the other agent will have 4 nodes within them, right? So they form like 3 clusters, and that agent is responsible to do every kind of computation for its own nodes. So suppose agent 1 has 3 nodes, right? Agent 2 has 5 nodes, agent 3 has 4 nodes. So agent 1 is responsible to sense information, to compute things, and then it will actuate that in its own 3 nodes. So it's a cluster based control. So each of these clusters can talk with each other. These agents can talk with each other, but the agents will only talk. The agents can't talk with a node of a different cluster or a different agent. So the three agents will probably talk with each other. They may talk, they may not talk. Depends on the communication protocol or infrastructure or topology. But each of the clusters, there are clusters formed in the distribution system, and within the cluster, they will try to solve their own problem. It's almost like international relations. So in India will solve its own solutions. India may talk with Russia or US at times, but it depends. But they will solve their own problem. Each of them will solve their own problem, and they will sense locally and do everything. But they will just talk with each other if needed. I mean, that need can be continuous, like all the time, or it can be in intervals, right? Or there can be no communication as well. Obviously, under wars, right? And distributed is another architecture. So in distributed architecture, you have, what distributed means is that you have this 13 bus feeder, right? In 13 bus feeder, each of the nodes are at the same level of priority. So in 13 nodes, if you remove the subsystem node, there are 12 nodes, right? So each of the 12 nodes are at the same level of importance. So each of the 12 nodes can talk with each other, um, can do their own solution. So each of the agents can sense information locally, like their own information. They can do local computation, but they can talk with each other. They can communicate with each other, but the communication is not with everyone. Like suppose there are 12 nodes in the system, right? So node 1 can only talk with node 2 because it's node 2 is a neighbor of node 1. Node 2 can talk with node 1 as well as node 3, but node 2 can't talk with node 4 or node 5, right? So it's like peer-to-peer communication, uh, and each of them will sense their own information, local information, and do local computation. But at the same time, they can talk just with their peer agent. And yeah, so these are four major architectures that we have in distribution systems. But there are other architectures as well, like you see the hierarchical architecture, right? So hierarchical architecture is probably the most prevalent in power systems. So in power systems, if you go to transmission system controls, then you have balancing areas, you have, so like in India also you have like 5 zones, right? North, east, south, west, and central. I think they got connected as a whole, or if south is right now out or something. But so generally power system, the big power system, it's, there are certain control areas, and each control area have even more sub control areas under them, right? So this is a hierarchical way of control architecture. This is the most prevalent in power systems, and This is what transmission systems follow, that you have control areas, and each of the control areas will have their own sub control areas, like under which they will, you know, control their own areas, and each again sub control areas will have even more sub control areas, like smaller ones. And hybrid is a mix of all of these three, all of these five, right? So, you know, it can be local, it can be decentralized, it can have a combination of local and centralized, it can have a combination of distributed and local, and all of that. Okay. Okay, I won't go into this details. Let me see why. Okay, I think I pulled up the wrong. I mean, the PowerPoint is kind of similar, but after this, I just wanted to show. So, um, so this is what a centralized voltage control looks like. So you have this substation transformer, then you have switch bank capacitors and energy storage systems, then you have photovoltaic system, load tap controller, and all of that. So centralized means I was talking about that in centralized you have ADMS, right? Or the distribution management system. So all of these agents will have these voltage meters, right? I've shown voltage meters, but it can be power meters. You can also take power meters as well. So all of these meters will send information back to the volt-var control scheme, where the volt-var control scheme will then, solve the power flow, and then it will, you know, not solve power flow, but it will solve a optimization problem, and then it will send the set points back to each of the agents. So so basically, it's centralized computation and communication, huge computation burden. So the computation burden is huge because suppose you have this 1,000 node system, right? 1,000 node distribution feeder, and you have this huge amount of measurements, and then there are the state variables that you have to, I mean, the control set points that you have to solve for, maybe will be in 200s or 300s or whatever, right? So you have this huge optimization problem that you have to solve within a certain time, because you have to give the segments back to them, right? Back to the control agent. So there is a certain time within which this computation has to be solved, has to be done. Now if the computation is not done within that time, then operators don't know what to send, right? And they don't know what to do with that. So it's a huge computation burden that we have for centralized. Scalability is an issue. Scalability means that how can this architecture work for increasing number of nodes? So this is what scalability means. Is it scalable? So suppose you have a centralized optimization algorithm. It works for 100 node system. It takes, like, suppose, I'm just giving an example. Suppose it takes 100 seconds to solve it. If you go to 1,000 nodes, will it grow the computation time, will it grow exponentially high, or it makes some sense, like it can solve within a stipulated time? Suppose if you increase the number of nodes, at a certain point you see that it's the computation burden is so high that it's not possible by supercomputers or whatever. I mean, they cannot come up with the solution within a computation time, right? So that's the scalability issue. When you have a huge problem to solve, not huge, but so there are certain classes of problems, optimization problems, or there are some classes of problems in, even if you look into CS, like computer science courses, There are certain classes of problems which are um, NP hard and all of that. So those classes of problems, sometimes if you increase the number of nodes or if you increase the number of problem variables, they are not able to solve within a computation within a certain time, right? So generally, the optimization problem that we solve in optimal power flow, if you ever write the equations down for optimal power flow, then that problem is generally NP hard. Now, there are definitely different kind of tactics and techniques that we use to make it, you know, it's NP hard and non-convex. Then we kind of use different kind of techniques, relaxations and approximations to make it convex and make it easier. But all of these things has to be tested a lot for increasing number of nodes. Otherwise, the scalability can be a problem. And the other problem is single point communication failure, right? So if there is a certain measurement or there is certain communication in a line that is very important for computation of these variables and that goes out, then there is a problem, because centralized architecture means it depends a lot on communication infrastructure. So the other one is local, as you know, as I told, like it's local computation, local communication, and so it is done locally, right? So if you have a capacitor and you say that, okay, beyond this voltage, don't switch on it, don't switch on the capacitor. If the voltage goes beyond 0.98, don't switch it on. If it stays below 0.96, then switch it on, like that. If you take this kind of rule based approaches, then you don't know what the impact is, what the impact of the capacitor is throughout the feeder, or maybe the next node, right? Maybe the next node was already at 1.05, and then suddenly you switched on the capacitor depending on your own rule based approach, right? Once you switch on the capacitor, that neighboring node which was at 1.05 per unit will can easily shoot up to 1.06 or 1.055 or whatever. Then there is an over voltage issue in the next neighbor node, right? So the problem with local voltage control is that the approach is local. It is easy to execute, it is easy to sense, not much to to compute and everything, but you don't know its impact network wide. And the solutions are also non-optimal because it's a rule based approach, right? You don't know if this is an optimal solution, optimal in the sense that if this result will incur the minimum amount of cost to the utility, or minimum cost to the customer or whoever the owner is, right? So this gives non-optimal solutions. And then you have distributed voltage control. So distributed voltage control is, as I talked about, is you have this different agents like switch capacitor banks and then load tap changers, PV controllers, and all of them. So in distributed control, you have distributed computation and communication. So distributed computation means that each of the agents are capable of doing computation on their own. Suppose the energy storage system controller, right? The energy storage controller can do its own computation. So it senses its local voltage, it can do its own computation, but at the same time, it can also communicate with, say, the switch bank capacitor, right? I'm giving an example, but it depends on how the feeder model is. But it can talk with the neighbor agent, it can communicate with the neighbor agent, and then use that information in its own computation algorithm. So energy storage controller will take its local information. It can also take information from its neighbor agent, and then after gathering that information, it does a certain computation. It can be an optimization problem, It can be just solving a set of algebraic equations, whatever there is. And then it sets the set point. I mean, it can give that set point back to the capacitor bank. That set point can be, you know, there are suppose three banks, switch off, three banks were on, right? Each capacitor bank was say 100 kVr. So initially it was giving 300 kVr. When you switch on one, it says, if the set point says that switch off one bank, so then now you're giving 200 kVr, right? So these kinds of set points, it can, change, and it can, that way, if the set points are changed, if the capacitor bank which are on are changed, then the voltage will also change, right, in the next instant. Because at 300 kVr, the voltage will be pretty high. At 200 kVr, the voltages will boost it down. It will go down a bit. So the other advantage that distributed has is it improves. It can be solved with. I mean, it can be done at improved scalability and robustness. So improved scalability, the reason it is the scalability is improved because in centralized you have all these measurements coming in, right, in DMS, and just solving a certain optimization problem. So it's a huge communication burden, computation burden. But here in distributed control, there is not much of burden because each of the agents are like have the ability to compute on their own, right? So you can think in this way that the centralized optimization problem has been, divided into various sub problems, and each of the sub problems are given to each of the agents. So that's why scalability is improved. So if you increase the number of nodes, the amount of the computation time that will be taken by the distributed control architecture won't go won't go exponentially high, which can be in centralized schemes. Robustness is improved in the sense that robustness in communication, because as I told, like one agent can talk with the peer agent, right? It can talk to peer. It cannot talk with other agents in the system, though it depends on how you create the communication infrastructure. But I'm just saying that if you have a distributed architecture, you say that I have this agent, and this agent can only talk with these neighbor agents and not with anyone else. Then robustness is improved because there is no communication exchange that is happening network wide, right? So to solve a certain, or to get to a certain optimal solution, you don't have to you know worry about what if this communication fails or whatever. And convergence relies heavily on hyperparameters, initial settings, problem formulations. So this is a very a bit deep down. So all these distributed algorithms will have different hyperparameters, will have different kinds of problem formulation, different kinds of initial setting, because all optimization problems are kind of dependent on the initial values, right? From which point you start to reach to the global optimal point. So that matters a lot. It also matters how hyperparameters there are in the algorithm, right? Hyperparameters in the sense that because you're going from iteration 1 to iteration 2 to iteration 3. Now if you don't choose the right hyperparameters to move from one point to another, then it can lead to non-convergence. Okay, so I have like 10 minutes, so I'll just jump over this thing, which is OpenDSS MATLAB COM interface. So why this is important is OpenDSS has the whole power system model with you, right? So you have the whole distribution feeder model in OpenDSS. Now, suppose you want to code an optimization approach. You want to code on your own, and you want to do it in centralized or local or distributed, right? OpenDSS has a good interface with MATLAB. So suppose if you want to do that, OpenDSS has a power system model, and you write the whole optimization engine in MATLAB. So what can happen is OpenDSS solves a power flow, gives certain information to MATLAB. Then in MATLAB, you have the optimization problem to solve, right? So in MATLAB, you solve the optimization problem and then say that, oh, if this is the situation, then I need this much of tap setting in this particular regulator, or I have to switch on this capacitor, or I have to switch off this capacitor. So this in this MATLAB, you run the optimization engine, and the optimization engine will give you all these set points, right? Now, how do you know if these set points will solve your problem, right? Suppose initially in OpenDSS, when you run power flow, there is a voltage issue. You send all the voltage measurements here in MATLAB. In MATLAB, you have optimization problem which gets solved, and then you send back the set points back to MATLAB. And if when you send to MATLAB, then these set points are supposed to mitigate your voltage issues, right? So we'll just see how OpenDSS and MATLAB interface works. So I'll give you an example like hands-on in IEEE 13 bus system. So it will be easier for you to understand. Mm. If you show how to obtain time series load flow results, magnitudes for all the nodes on a per minute per second basis. Okay. Okay, for the time series, I don't have the code written with me right now, but you know, if you search it in OpenDSS discussions, you'll definitely find it. So the mode that I showed was snapshot, right? But the mode can be set at yearly, monthly, hourly, 15 minutes basis or something like that. And then when you run the whole power flow with that particular mode, then you can get the whole profile to yourself, and you can just you know, export that to CSV. But I can show the CSV again. So yeah, so you can so when the mode, if you change the mode to hourly, it will do all the job. So then when you set the mode to hourly, then you have to put a load multiplying factor as well. So um, you can look into the discussions, OpenDSS discussions. I'm sure there is something, and if you don't find any, then I can take a look. Okay, so let me go to this folder. So as you see, so this is one folder that I created like yesterday. So this folder has two DSS files, right, which was initially there in IEEE 13 bus system as well. And I have created like two MATLAB codes just to show how tap changes work and all of that. And so this is just to show how the MATLAB COM interface works. So basically, it's the same. Um, so so here it's a tapchange.m file, MATLAB file, and DSS startup, start. Okay, these are some basic files that you have to kind of write it down in order to create that interface. And so in DSS text command, so in DSS text command means, whatever command you kind of put it here, it connects that with OpenDSS. So you set the path or the location of that file, and then if you go, so inside this folder we also have this IEEE 13 node circuit.dss, right, which is just here. So when you say compile, it compiles the whole DSS circuit, a DSS file. So it compiles it. Here I've taken a snapshot. Mode is snapshot. Load multiplying factor is 1 right now. So what I mean by load multiplying factor is that you multiply that factor with each loads in the system, because the test results that you saw, that so the multiplying factor gets multiplied with each load in the system. If it is like 1.2, it multiplies by 1.2. If it is 1, so it's like the basic one that you already saw in that manual. Now here, suppose you have this. Suppose you have this. You have this optimization engine and everything, right? Optimization engine and everything. And then this optimization engine gives you certain set points, right? It gives you certain set points. And then you want to put the set points back to OpenDSS. So what do you do? Suppose I'm giving an example of a regulator, right? So I am fixing, so here I'm fixing whatever set points I got here, right? I can just put it here. So if the tap setting suppose is say 9, then it is 9 multiplied by 0.00625 plus 1, right? So you can put the same tap settings here. So these are the control commands for regulator tap settings. And then okay, let me do this. This part. So okay. So once you have the optimization, code done with you, right, and then you get a certain tap setting of a regulator, right, and then you put that set point right here, right here. If you do that, then what it does is that it fixes the transformer, the the regulator tap settings. Now, if I want to run this, then what it will do is it will go into this particular folder, look into IEEE node circuit.dss, and it will fix the transformer settings, the regulator tap settings right here. And then we can check how the, so then what I've done is that after it does that, then it solves power flow, dss solution.solve, it solves power flow and everything. And then I'm displaying the same regulator tap settings, and I'm also looking into the voltage, voltage phase A. So what this does is that, because you have multi-phase distribution system, right? So it takes phase 1, phase 2, and phase 3. So phase A, phase B, and phase 3. So let's just run this. So you see that, because it's like the regulator tap setting was kept at 1.05625, right? So it fixes the tap settings 0526, 1.0526 and 25, and then it runs powerflow in OpenDSS, and then OpenDSS gives this regulator tap. So this is just to confirm. Then you see that we are also importing voltages from OpenDSS, right? If you see that there is this boost that is happening, and this is exactly what we wanted, 1.05625. And then you get all this voltage boost. So suppose it was in phase B, I wanted 0.0375. So it's pretty much similar to that. And then at the end, I also wanted to know where capacitors are present. So there is this also code that I put in that, find out capacitors in the system and just display the names and then where the nodes, which nodes are connected to. It also gives the capacitor information. So there is this capacitor 1, which is connected at 675. In all the phases of 675, 1, 2, and 3, and they were 200 kVA each, right? And there is this another capacitor, which is capacitor 2. It's connected at 611.3. So it is phase C of 611 node. And the rating was 100 kVA, right? So this way, you can. So this is an example of how to interface MATLAB with OpenGIS. Now this interface can be done also with Python. So there is this package called PyDSS. So if you write your optimization code or any kind of approach, whatever you want to do, you write that in MATLAB and Python, and just interface with. Why the interface is needed is that when you want to send some information, if you want to change some set point, then you can send that set point back to OpenGIS. Now think in this way, that you have an optimization approach or optimization problem written down in MATLAB or Python, and then you are running a one-day scenario or one-day power flow in OpenGIS. So at every instant, OpenGIS will send voltage measurements or what kind of measurements you need for the optimization approach. The optimization approach will give you set points, and that set points will be sent back to the OpenGIS, right? And it will improve voltage or whatever happens, right? So you can see how you can then check how your control approach affects the grid directly. And the distribution grid that is modeled in OpenGIS is non-linear. So whatever approach set points that you get as the result, you can see the real actual, result of that actuation on the real field. Now let me try another thing. So this is just changing the regulator tab settings, right? And I'll try to show another case. So I'm trying to show another case where I'm changing capacitor controls. So okay. So here, what I'm trying to do is, there is this capacitor, right, which is at 611. Now in 611, if you saw in 611.3, there is this capacitor which was 100 kVA, right? So at 611.3, there is no phase B in 611. There is no phase A in 611. So there is only phase C. In phase C, the node voltage is 0.9608, right? Now, if I increase this capacitor from 100 kVA to 200 kVA, then it is injecting more reactive power, right? So the voltage should be boosting. So let's just try that. So what I'm doing here is that I'm setting a new set point, say 200 kVA, and the capacitor on is true. True meaning that the switch is on, and then I'm putting the DSS text command. So it is editing that capacitor value and editing the status of the capacitor in OpenDSS. So this is what it means. And then you have I'm solving power flow. and then I'm taking this modified capacitor information, all of this. Sometimes this code, this is a query code, so sometimes this query code doesn't work. But anyhow, what we want to see is, does the voltage boost or not using this increased amount of kVr. So just run this. Okay, see now that your voltage has been boosted, right? It was like initially it was 0.9608, now it's 0.97. Now you can do it in differently. You can here I've just shown voltage, right? You can also check in terms of measuring power flows, right? Just in front of the capacitor you put a meter, and then the meter, in the meter you measure active and reactive power flows. And obviously with a 100 kVr capacitor and a 200 kVr capacitor, your reactive power flows and active power flows by a very small bit will also change, right? So you can put a meter also, but this is a very good representation. Now if I want to change it, say 300, so it's now 0.977. So it's like 0.995, right? So it kind of works. And